Leading the new generation of ultimate rides was Superman the Escape. In 1999, it broke the world record for the fastest and tallest thrill ride. Driven by 2,000 horsepower and precise computer programming, Superman's 6-ton trains accelerate from 0 to 100 miles an hour in 7 seconds. That's 2.5 seconds faster than a Porsche 911 Turbo. Passengers are propelled along a 280-metre horizontal track towards a vertical tower.
We wanted to do two things. We wanted to build the fastest thrill ride anywhere in the world and break the 100-mile-an-hour barrier. And we wanted to be the tallest thrill ride in the world, and we did that when we came out at 415 feet.
The incredible momentum created by the launch carries the train up the 127-metre tower, higher than a 41-storey building. The train nears the top of the tower, gravity overcomes momentum and the passengers return to Earth backwards. Once the train returns to the horizontal track, the same motors that launched it act as brakes to bring it to a smooth stop. To achieve the astonishing acceleration, Superman's creators looked beyond the accepted propulsion methods. Since the 1850s, traditional roller coasters, like this wooden one, have relied on gravity as a propulsion system. The speed of the ride was dependent on the height of the first drop. To achieve the 127-metre world record, Superman would have had to have had a first drop of more than 240 metres. It would also require a huge amount of space.
If you wanted to have a traditional roller coaster with a normal lift that you're used to seeing, in order to get a 415-foot height, your lift would have to be in excess of 800 feet long. And when you take into account that a chain is going to have to go up that lift and down that lift and the other configurations it's going to need, the weight of the chain alone is going to require motors and gearboxes and arrangements that would just make it practically impossible to use conventional chain to do.
To get round these problems, Superman's designers chose a revolutionary propulsion system, linear synchronous motors. These electromagnetic motors were developed to launch missiles as part of the Star Wars defense system.
The linear synchronous motor challenge was a tremendous challenge, actually. It had never been used in any commercial application at all. There had been some work in a military application for linear synchronous motors. So when we brought it in and started to apply it, we had a lot of obstacles to overcome.
The secret behind linear synchronous motors is magnetism. Magnets on the track repel opposing magnets on the bottom of the train, lifting it up, so the train floats on a frictionless magnetic field. To create forward momentum, computers control the polarity of the magnets in the track so that they alternately attract and repel the magnets in the train. This rapid attraction and repulsion means Superman's motors both push and pull the train forwards. This system is so effective it can accelerate the train to 174 kilometers an hour in just 7 seconds.
We're pulling the car through the front of the magnet and pushing the car out the back of the magnet. That requires a tremendous amount of processor speed and the ability to switch large amounts of electricity in order to make that electromagnet do it. Coming up with a computer network that was reliable enough and quick enough to make that switch gear move that power in the motors was the challenge that we had.
Go! Superman riders experience the sensation of being pinned to their seat, followed by the feeling of weightlessness. These sensations are what provide the thrill in thrill rides, and what creates them are G-forces. A few G-forces can be exhilarating, but the human body can only endure so much before we pass out. And in extreme circumstances, G-forces can even kill. Human beings all live daily with G-force. A force of 1G is the force of the Earth's gravitational pull that a person feels when they're at rest on the Earth's surface. In other words, a person would feel their normal weight. However, when an individual experiences higher than 1G, they feel heavier, equivalent to the number of Gs. At 3Gs, they would feel 3 times as heavy. When a person feels weightless, they're experiencing 0G. Tim Burkhart explains.
When a rider rides Superman, there's obviously 2 prominent G-forces that they're going to experience, positive Gs and negative Gs. The positive Gs really are what you feel during that tremendous boost of acceleration. You're just being pushed back into the seat, and you get that feeling of rocket launch or being launched off an aircraft carrier or riding in a race car. It's just a great feeling being pushed back into the seat. And then conversely, when you're coming down the drop, those forces work the opposite direction and are negative forces that create the weightless feeling. And again, on Superman, you get almost 3 seconds of weightlessness, and virtually every roller coaster built has some degree of weightlessness to it, but it's typically measured in tenths of a second. On Superman, you're going to experience for about 3 seconds.
This weightless feeling creates the bottom out of the seat experience, what thrill riders call airtime. Watch the breast pocket of the man in the middle of the car. At the moment of 0G, he stops with the train because he's held in his seat. However, his sunglasses, which are not strapped in, continue to travel in a straight line upwards. If the man was not restrained, he would join his sunglasses. Research on test pilots has shown that humans can only tolerate small amounts of negative G, because while accelerating downwards, the liquid part of your body, blood, lags behind the solid parts, bones and organs. Too much negative G will cause a rush of blood to the brain, and the pilot will literally see red and then collapse in what is called a redout. More positive G than negative, but even so, designers have to work within limits. If a healthy person is subjected to too much positive G, they will start to lose their vision at around 6G, and at 9G blood will flow from the brain and they will black out. At 14G, they will die.